Alright, let's do some moon or bust. Let me find something cool to listen to for this. Alright, let's check this out. Here we go.
I have good news and bad news. Bad news first. 2 years ago, we reported on the crisis in cosmology. Since then, it's only gotten worse. And actually, the good news is also that the crisis in cosmology has actually gotten worse, which means we may be onto something. The most exciting thing for any scientist is when something they thought they knew turns out to be wrong. So it's no wonder that many cosmologists are starting to get excited by what has become known as the Hubble tension for the crisis in cosmology. The crisis is the fact that we have two extremely careful, increasingly precise measurements of how fast the universe is expanding, which should agree with each other, and yet they don't. We first reported on the growing hints of this tension 2 years ago. Back then we expected the new refined measurements would bring the numbers into agreement. So far that's not been the case. But just recently, one of these methods received a massive refinement due to the Gaia mission and its unprecedented survey of 1 billion stars in the Milky Way. And guess what? The tension is now even tenser. So, is it time to rethink all of cosmology? Before we can even think about doing that, we should probably do a refresher on what the issue actually is. So, you may have heard that the universe is expanding. Space on the largest scales is stretching, throwing galaxies apart from each other. We've talked about how astronomers first figured this out. Long story short, when a distant galaxy's light travels to us through the expanding universe, it gets stretched out. Its wavelength increases. If we also know how far that light traveled, the distance to the galaxy, then we can figure out the rate at which space is expanding, at least along the path to that galaxy. Combine the redshifts and distances of many, many galaxies, and you have the expansion rate of the universe, typically expressed as Hubble's constant, after Edwin Hubble, the guy who first properly measured it back in 1929. By comparison, getting distances to a galaxy is much, much trickier than getting redshifts. It depends on a long chain of distance measurements that we call the cosmic distance ladder. First, you measure the distance to objects in our solar system. Then you use those to measure distances to nearby stars, then more distant stars, then nearby galaxies, then distant galaxies, etc. If one of those distance measures is wrong, then all subsequent rungs of the distance ladder are off. Hubble's distance measurements were based on a method pioneered by Henrietta Swan-Leavitt. She developed one of the first so-called standard candles. These are objects whose true brightness or luminosity can be known. Knowing the true luminosity of an object means you can figure out its distance just by observing how its brightness has been dimmed by that distance. Swan-Leavitt realized that a type of pulsating star known as a Cepheid variable has a rate of pulsation that depends on its luminosity. Measure the pulsation rate and you know its true brightness so you can find its distance. And if the Cepheid is in another galaxy, you have the distance to that galaxy also. Cepheid variables are great standard candles, but they're just stars. They are too faint to see beyond a certain distance. In the 1990s, two teams of astronomers employed a new type of standard candle, the incredibly bright Type 1a supernovae that result when a white dwarf star explodes after cannibalizing its binary partner. Using these supernovae to get distances to galaxies halfway across the universe, they found something totally unexpected. Not only is the universe expanding, but that expansion is accelerating. And so dark energy was discovered. a mysterious and ubiquitous energy that grows as the universe grows, speeding up its expansion. Dark energy very likely holds deep clues about the fundamentals of reality. With its discovery, it became very important to perfect our measurements of the expansion rate.
We'll try it.
Both to
We'll
confirm
see how it
dark
does.
energy's existence and to learn of its true nature.
All right.
And this is where our story splits. There are, broadly, two approaches to improving that measurement. One is to double down on the old method, find more Type 1a supernovae and improve those distance measures. The other is to find a totally independent measurement of the expansion rate. A good reason to do that is that the supernova method is a pretty high rung on the cosmic distance ladder, which means that if any rung below it is broken, the method fails. So, different teams of astronomers pursued both approaches, and this is where the crisis emerged. One alternative method for getting the expansion rate is to study the oldest light in the universe, the cosmic microwave background. This light was released only a few 100,000 years after the Big Bang and carried with it vast information about the universe's early state. Now, I'll leave you to watch our previous video on the subject to see how our map of the CMB using the Planck satellite can give us the expansion rate. The Planck team calculated a Hubble constant of 67.6 kilometers per second per megaparsec. Let's not worry about the weird units right now, but they also claim an uncertainty of about 0.5%, making it the most precise measurement of the expansion rate ever made. Meanwhile, Adam Rees, one of the Nobel-winning discoverers of dark energy, has doubled down on the supernova method. A couple of years ago, his team published a new Hubble constant of 73.5 plus or minus 1.5 kilometers per second per megaparsec. That's in the same ballpark as the Planck result, but far enough off to raise many eyebrows. One possible explanation for the difference is that the nature of dark energy has changed over time. The Planck team's Hubble constant assumes that dark energy has had a constant density for the entire age of the universe. Now, that's what you'd expect for the simplest models of what dark energy might be. But if dark energy has changed over time, it could explain the discrepancy and indicate that dark energy is even weirder than we thought. It's hard to overstate how huge a discovery that would be. So you can see how it might be nice to find out one way or the other if the difference between the Planck and supernova results is real. Most people still think that there are unknown errors that are affecting one or both. For example, the cosmological distance ladder could have a broken rung. The supernova standard candles are calibrated based on distances from our good old Cepheid variables in galaxies where both are observed. But those distant Cepheids are in turn calibrated based on Cepheids in our own galaxy, which we can get by a method that's much more reliable. That method is stellar parallax, and it's about as direct a method you can get besides building a giant space ruler. Ultimately, refining the supernova distance measurements comes down to refining parallax measurements, and that's what we've finally achieved. You are already familiar with parallax. Place a finger in front of your eyes and blink left and right. Your finger moves relative to the background, which I guess is me in this case. Now, move your finger away and the displacement is less, closer, and it increases. We can use this same trick to measure the distance to stars. As the Earth orbits the Sun over the course of a year, nearby stars appear to move relative to more distant stars. That's stellar parallax, and our quest to measure it has been central to our understanding of our universe for hundreds of years. Prior to the invention of the telescope, the fact that we didn't see obvious stellar parallax was taken as evidence that the Earth is not orbiting the Sun. It turns out that the stars are just so far away that you need careful observations with quite a good telescope to see parallax in even the nearest stars. And so it was that in 1912, Henrietta Swan-Leavitt used parallax measurements of Cepheids in the Milky Way to turn these stars into standard candles, and so founded our distance ladder, which ultimately led to the discovery of dark energy. But this feels a bit like a house of cards. The ladder was entirely dependent on the relatively few Cepheids that are close enough for parallax measurements. Things started to get better when we put telescopes in space. Above the blurring effect of Earth's atmosphere, it's possible to make better position measurements. The Hubble Space Telescope has done great work here, and so has the European Space Agency's Hipparcos satellite. which track the motion of 100,000 stars in our local patch of the galaxy. But to really nail down the lowest rung of the distance ladder, we need a lot more Cepheid parallaxes to much greater distances. And that's what ESA's Gaia mission has given us. Parked in an orbit just past the moon, Gaia scans the sky year after year, mapping the structure and the motion of a good fraction of the Milky Way galaxy. Gaia is making the most accurate catalogue yet of stellar parallax measurements. For the nearest, brightest stars, it's 200 times more accurate than any previous measurement. Gaia has allowed us to recalibrate Cepheid variables as standard candles, which in turn enabled a recalibration of Type 1a supernovae, which in turn gave Adam Rees and team a refined measure of the Hubble constant. So, what do you think? Do the supernova and Planck results agree? Not in the least. The Gaia-based Hubble constant of 73.2 kilometers per second per megaparsec seems to confirm the previous Type 1a supernova result, now with more surety about the distance ladder it's based on. Now, before we start jumping up and down and yelling about new physics, remember that we are level-headed scientists. 2 independent methods aren't enough. We need more, and we have some great options that will either break the tie between Planck and supernova, or confirm that the difference is real. We've already talked about one of these options, is to look for vast ring-like patterns in the way galaxies are scattered across the universe, and use those rings as a sort of standard ruler. These baryon acoustic oscillations are the fossils of ancient sound waves that reverberated through the hot, dense plasma of the early universe. Now those ripples are frozen into the distribution of galaxies that formed from that matter. The baryon acoustic oscillations seem to be coming on the side of the Planck result, a Hubble constant in the high 60s. Another extremely promising method is from gravitational constant. That's the bending of light around massive objects due to their warping of space-time. One manifestation of this is when a distant quasar, a giant gas-guzzling black hole, happens to be closely aligned behind a more nearby galaxy. Then, that quasar's light travels multiple paths through this gravitational lens, resulting in multiple images of the quasar from our point of view. Quasars are violent beasts. The maelstrom of gas fluctuates in brightness as it spirals into the black hole, and so we see the lensed quasar images flickering. But they flicker out of sync. There's a time offset due to the fact that these different paths through the universe have slightly different lengths. By measuring the time delay in these flickering lenses, we can get a measurement of cosmic distances, and with that a measurement of the expansion rate that's independent
Let's see how
of the
this
cosmic
does.
distance ladder. So far, we've only done this with a small number of lenses, and so the uncertainty is large, but published results give a Hubble constant in the low 70s, so in agreement with the supernova runs. But this game is about to take off with upcoming giant surveys set to discover thousands of new lenses that should massively improve this measurement. And before too long, we may even be able to use gravitational waves from emerging black holes to measure the Hubble constant. These waves get stretched by the expanding universe just like light does, but unlike light, they also encode information about the distance they've traveled, and so can be used to measure the expansion rate without the cosmic distance ladder. We're calling these black hole mergers standard sirens, and while the error bars they give are still very large, they'll only get smaller over time. That is where the crisis stands. It's increasingly clear that there is a hole in our understanding of the universe.
Like I need some stability.
Whether it's a crack in a rung of the cosmic distance ladder, or something
Oh,
more fundamental about how the universe expands.
Oh no!
Scientists love being wrong, because when you find the source of that wrongness, it can only lead to greater understanding.
Alright, let's add some stability.
In this case, of the strange forces driving our ever-expanding space-time. As always, I want to give a huge shout-out to all of our Patreon supporters. Your continued support is such a huge help. If anyone would like to pitch in, even a couple of bucks a month makes a real difference, and also gets you access to the Spacetime Discord, where you can nerd out 24/7. And today's extra special shout-out goes to Sandy Wu, who's supporting us at the Big Bang level. Sandy, these are such strange and uncertain times. I mean, seriously, we don't even know what Hubble's constant is. But your support grants some much-needed stability to space-time. I mean, the YouTube show, not the expanding fabric of the universe, that is still freaking people out. Today, we're doing comments for the last 2 episodes in which we explored the connection between gravity, light, and the flow of time. Time Bucks asks how we can be traveling at the speed of light in the time dimension? Well, I'm glad you asked, because this notion gets stated without much justification. The idea is that massive objects travel through time at the speed of light.
See how that does.
It's just one way, really, to interpret the math of special relativity. In relativity, there's a thing called the space-time interval, which describes the separation between two events in space and time. It's the minus of the sum of the squares of x, y, and z spatial intervals, plus the square of the time interval times the speed of light. You need the speed of light in here to give time the same dimensionality as space. Your velocity through space-time, also called your full velocity, is just a change in the space-time interval divided by the change in time. But if you're motionless, then you have no change in the space intervals. And so your full velocity is just c times delta t divided by delta t, or just c, the speed of light. So that's where the idea comes from in the math. But what does that mean physically? Does it mean anything physically? Well, that's less clear, because we don't really know what time is, nor space for that matter, or whether they're really the same type of thing, dimensionally speaking. We would also need to justify why the c in the space-time interval has to be the speed of light. It's worth a full episode to explore this one, and we'll definitely get around to it. But if you want a much better description of the math than I just gave, check out Sabina Horstmann-Feller's episode on this, link in the description. John Smith noted that Huygens' principle seems eerily similar to the double-slit experiment if there were an infinite number of slits. Well, John Smith, you're in good company. There's this story of a young physics student hearing the description of the double-slit experiment, in which the professor describes how you could figure out the interference patterns by thinking of circular waves originating from the slits and calculating how these ripples add up at the screen. The student raises his hand and asks, but what if you had 3 slits? So the professor says, well, you just add up the ripples of 3 waves. The student then trolls the professor further with, what about 4 slits? Which they reply with, obviously you add up the ripples of 4 waves. And then what about 5 slits, etc. Until finally, what about infinite slits? That student was Richard Feynman, or so the story goes, and he just figured out the Huygens or Huygens-Fresnel principle all on his own a couple of centuries late,
Probably needed some more
but
control.
independently nonetheless. So, John Smith, you're another 100 years late, but good work anyway. Tom Karawish and Clear Night Sky saw the Feynman connection also, pointing out that the Huygens principle feels like Feynman's path integral formulation of quantum mechanics. For those who don't know, the path integral calculates the trajectory of quantum objects by adding up all the possible and even impossible paths between 2 locations or states. The unlikely paths cancel out, leaving you with a prediction for the path it'll actually take. We actually did an episode, search for path integral on the channel homepage. But it seems that Feynman was influenced by Huygens-Fresnel and as well by the principle of least action. So yeah, nice work reinventing all of physics, guys. Several of you commented that this whole gravity bending light thing might explain why stormtroopers have such terrible aim. I think you may be onto something, if you think about it. These poor guys have to fight in so many different gravitational fields, Star Destroyers, the Death Star, forest moons, ice planets. Must be hard to recalibrate every time. Who knew that George Lucas was such a Jedi master with general relativity? But the whole series actually makes much more sense when you think about it. For example, when Greedo shot beforehand in the updated releases, we were really just watching the same scene from the perspective of a passing Star Destroyer in hyperspace. Its superluminal motion reversed the apparent causal ordering. Or, in other words, shot first, and did.
You do not see the real world. Your eyes are lying to you, or more precisely, your brain. In 2011, scientists at New York University ran a study which showed that we may perceive threatening objects to be closer than they really are. In January this year, researchers at the University of California found that in an effort to create a continuous image, our vision is stuck up to 15 seconds in the past, as do YouTube videos, so our brains need time to buffer. And finally, the sun is green. At a young age, we learn we mustn't ever look directly upon it. But those that dare, perhaps to witness the fleeting beauty of a sunrise, gaze upon a warm, yellow orb that gives life to most species on Earth. This color is not a trick of the eye, but a trick of the air. Molecules of nitrogen and oxygen scatter blue light away from us all, making the sun look redder than it truly is.
Didn't have to do that, but I just kind of wanted to.
And to the human eye, the sun would appear the purest white, a combination of every wavelength of color it emits in different quantities.
Alright.
And this is the lie, the color white created in our minds. Objectively, the sun is, of all colors, green, emitting more green photons than any other wavelength. And that is not the only way our eyes deceive us in regards to our closest star. Ultraviolet rays that tan our skin, infrared that warms our faces when we step out on a sunny morning, radio waves which can be picked up by our technology. Our sun is constantly producing massive amounts of photons that stream around and through us at wavelengths our eyes simply did not evolve to perceive. These limitations mean we bathe in a constant wash of particles that we simply cannot see. And this hidden world is not only made up of light. The sun also produces massive waves of particles that are so unresponsive as to have been completely undetected or even conceived of until the 20th century. And yet, are so numerous that across the universe they outnumber the particles that make up ordinary matter 1 billion to 1. It is with these neutrinos we may be able to answer some of the deepest questions about our cosmos. The oldest light in the universe, the cosmic microwave background, is 380,000 years younger than the Big Bang itself. Before that, the universe was too hot and too dense for light to travel freely. But if the oldest images of the cosmos are still 380,000 years old, how can we ever know what happened before? What if we want to know what the universe was like, not just in its first year, but its first second? Our telescopes cannot tell us. They have reached an opaque barrier they cannot penetrate. Yet astronomers have found a way to pull back the veil, to uncover these early moments in time, pushing back the clock to the most ancient map of the cosmos there is.
Let's just go ahead and stage.
But to do that, they will first have to
I guess
probe
it'll work
the
better if I just don't have that
these
giant weight.
cosmic ghosts, secrets that challenge our very understanding of how the universe works. This video has been kindly sponsored by BetterHelp. Many scientists believe the universe is infinite, and that can get lonely sometimes. BetterHelp is an easy-to-use platform that helps you access therapy from your phone or computer. The last couple of years have been difficult for everyone, and it's so important to not only stay physically healthy, but mentally too. One of the barriers for me had always been that in times of crisis, I didn't know how to find someone to talk to, so it felt easier just to ignore it. BetterHelp are a great solution to this problem with over 20,000 therapists with a broad range of expertise, just a click away. All you need to do is access their platform, fill out the questionnaire with your specific needs, and BetterHelp will match you with a licensed therapist to listen and help you. It's convenient, straightforward, and trusted by more than 2 million people who have signed up and tried it. So, head over to BetterHelp, that's betterhelp.com/HOTU for 10% off your first month. Thanks again to BetterHelp for supporting education on YouTube.
Oh, did I really just like use like an in-atmosphere engine or something?
Why would you build
Something
a
stupid?
telescope inside an aeroplane? It is the morning of December the 1st, 2010.
Oops.
At the end of its 10-hour flight, a retrofitted
have the stages screwed
One
up.
change is instantly noticeable. Peering
I'll
out
pay
of the
attention next
tractable
time.
door at the
Hopefully that
rear
didn't screw up my
rests the 20-ton,
burn too much.
2.7 meter wide mirror of the Sophia infrared telescope. When the weather warms, it flies south for a second winter. From Palmdale to Christchurch, New Zealand,
watch
the
this.
annual migration allows access to an entirely different part of the sky. During its observation periods, as many as 100 flights a year, Sophia flies at an altitude of 12 or so kilometers, not all that higher than most commercial flights, and in doing so, it captures a light that the air beneath it would block. Water. It not only forms clouds which block visible lines of sight, while it looks clear to us in small quantities, entire oceans reveal its true nature. It appears blue because it absorbs red light, and it also absorbs invisible infrared light. Infrared light that holds the universe's most distant secrets. As the universe expands, light stretches, and after enough time, much of it arrives to the infrared. When Sophia flies, 99% of the planet's water is beneath it. The telescope can catch wavelengths of light that would never make it to other equipment on the ground. Wavelengths
Right,
that
I know
denote
that's
the
good enough,
births
so.
and deaths of stars, the formations of planets, and even dust surrounding
See how that goes.
supermassive black
So
holes
far I'm pretty
at the
screwed
heart
up,
of
so
galaxies.
we'll see.
For more than a century, humanity has had to use technology to overcome the limits of our perception. Telescopes can reveal to us the massive made insignificant through distance. Microscopes magnify what is under our very noses. The smaller the object of study, the smaller a wavelength
Well,
of
let's see how
light
this
you need
goes.
in order to study it in detail. Electron microscopes can achieve resolutions 4,000 times smaller than any optical microscope. But how do you study, or even detect, the smallest known particle in the universe? A particle so small, we don't actually know how small it is. In late 1951, Frederick Raines and Clyde L. Cowan Jr. began Project Poltergeist, the first experiment in neutrino physics. 2 decades prior, the physicist and mathematician Wolfgang Pauli had proposed the concept of the neutrino. He sought to balance an equation governing the process of nuclear decay.
Alright, here we go.
In some unstable nuclei, a neutron will spontaneously transform into a proton and an electron. The exact amount of energy was based on the principle of balance. Add up all the energy in the particles at the start of a reaction, and it should equal the total energy of all the particles present
Let's get
at the
to
end of
orbit.
it. But the electrons experiments were catching all came up wanting. Either the law of energy conservation was wrong at this level of subatomic particles, or another source of energy was missing. Perhaps, as Wolfgang Pauli first proposed, there was an even smaller particle which the neutron had broken up into. A particle neutral in charge, which escaped the nucleus, but also escaped capture. Direct detection of these neutrinos was deemed essentially impossible. They were simply too small and too ghostly. 100 trillion of them stream through your body every single second, as if you were simply not there. In fact, Pauli once said of the neutrino, "I have done a terrible thing.
Getting
I have
closer.
postulated a particle that cannot be detected." But it was the nuclear revolution of the 1940s that eventually proved him wrong. A child of Russian
Alright,
immigrants,
here's
Frederick
a
Raines
really
was born
bad
in a
orbit.
small New Jersey town in
I'll
1918.
circularize
As a
like
boy,
over
he
here.
developed a love of music, singing in particular. But his love of science grew from a moment of boredom in school where he looked out a window and noticed the splitting of light, known as diffraction. Raines' passion eventually led to a PhD in theoretical nuclear physics, and he joined the Manhattan Project in 1944. Over the years, he rose up the ranks to eventually head nuclear weapons testing in the Pacific. It was during a sabbatical that he realized the nuclear fission reactions provided by the deadliest bomb known to humanity could provide the concentration of neutrinos needed
Alright,
to
here we go.
detect one of them.
Circularizing. Ooh,
Still, he likened it to
Right
listening
there.
for a gnat's whisper
That's pretty good.
in a hurricane. As the 1950s dawned, Project
I want
Poltergeist
to
planned to
land
capture the elusive particle for the very first time by detonating a 20
somewhere.
kiloton
So,
nuclear payload,
I'm
which
going
could
to
provide a surge of neutrinos in sufficient quantity that maybe a mere
Just gonna go ahead
handful
and
actually had a chance
keep
of being
firing
picked up
retrograde.
by a detector placed a mere few meters
Excuse
away
me.
from the explosion.
Until we have a good
This detector was filled with a special mix
Good
of
landing
liquids
spot,
that
like
would
in the sun.
flash in rare circumstance, the creation of a charged particle after a neutrino collision, 1,000 times larger than previous detectors. They named it
let's just go for there.
El Monstro. Thankfully, Rains and his colleagues realized that if they added cadmium salts to their liquid, they could make it even more sensitive. A bomb would no longer be necessary. A nuclear reactor one could turn on, leave running, and turn off became the more sensible option. And in June of 1956, Rains sent a
Let's
communique.
just call it there.
A neutrino collision had been detected. Neutrinos were no longer theory, a mathematical concept used to balance the equations of the universe's inner workings. They were real, if barely tangible. Nearly 4 decades later, Rains was awarded the Nobel Prize for his work. Nowadays, modern detectors make their neutrinos a little differently. The Microboon experiment at Fermilab and upcoming Dune project employ liquid argon as a detector, and Fermilab creates neutrinos using a particle accelerator. But not all detectors need to make their own neutrinos. Some are on the hunt for those crafted by nature itself. The Ice Cube array in Antarctica features 86 cables drilled into the ice, encompassing a total volume of 1 cubic kilometer, equivalent to 1 million swimming pools. Since opening in 2011, Ice Cube has hunted for the rare neutrino, which has traversed billions of light years. For any and all of these projects, the important factor is shielding. Neutrino detectors are hidden in mines, underneath hundreds if not thousands of meters of rock, or, in Ice Cube's case, solid ice. This prevents other small particles raining down on Earth from causing interference, cosmic noise that would otherwise drown out the minuscule signal a handful of neutrinos every so often deign to give. But the question remains, just why are neutrinos so incredibly hard to detect? And why does that make them ideal for detecting the earliest moments of the cosmos? In your entire lifetime, the likelihood of you interacting with a neutrino is about 25%. Not bad odds, you may think. And yet, 100 billion pass through your thumbnail every second. About 180 million billion neutrinos produced only
Use
by
up
our
some of this
sun pass
fuel on
through
this
the Earth
before I
every
ditch it.
minute. A light year of
Slow me
lead
down a little
would
bit.
only stop half the neutrinos passing through it. Generally, neutrinos simply
This burn
do
is just
not
to get me to
interact with other
fall more
particles, be
vertically.
they matter or be they light. The 4 fundamental forces of gravity, electromagnetism, and the strong and weak nuclear forces govern how particles interact with one another. Gravity draws everything with mass together, like tiny beads rolling along depressions of space-time created by the presence of others. The greater the mass, the deeper the depression, the greater the appearance of gravitational pull. For a long while, neutrinos were thought to have no mass whatsoever, just like photons. While they could fall along the curves in space-time, they left no tracks of their own for other, similarly small particles to notice. Yet photons are the messengers of the electromagnetic force. Anything with electric charge, in our day-to-day, anything that's made of protons
little bit
and
more
electrons, interacts with the
burn to
electromagnetic
get
force
vertical.
to some degree. But neutrinos are the ultimate neutral particle. They are not composed of smaller pieces and are neither influenced by electric nor magnetic fields. Tiny neutrinos
Alright, we'll go ahead
simply
and
slip
stage.
through gaps. Of course, the mysterious substance called dark matter is invisible to the electromagnetic force, but at the very least we can see its gravitational influence. The strongest of the forces is the strong nuclear force, which has the job of binding together fundamental particles called quarks, and as a byproduct holds together neutrons and protons that make up the nucleus of an atom. Neutrinos, however, are not quarks.
I think I did
And
use
so the strong force too is
the wrong
heavily
kind of
ignored.
engine here. I think I was an
The only
idiot.
fundamental force
I saw
that
the
neutrinos
scoops.
appear to be ruled by
I'm so
is the
stupid.
weak nuclear force. Indeed, this was the very reason Pauli predicted their existence as the weak force needed to create them to maintain a balance of energy. In this way, neutrinos are ghosts, barely skirting the laws that govern our reality.
I tried. I'll try again.
They exist to
I guess this is
explain
gonna be an
why
or
the
bust.
energies of certain particles and certain reactions that we really can measure look the way they do. But that does not mean that they are exclusively cosmic duct tape, injected into physics merely to make our equations look nice. We can use them as probes, studying some of the most extreme events
Goodbye, Kerbals.
in the universe.
Oh no!
On February the 23rd,
Boom, boom, boom.
1987, 168,000-year-old explosion
Alright, I know what to do.
struck the Earth. An international effort hunted down the culprit. In the Large Magellanic Cloud, a dwarf satellite galaxy of the Milky Way, the nuclear furnace of a massive star had failed. A gravitational implosion concentrated enough of the star's mass for
Derp.
one last death whale. A supernova. But hours before the light of this cosmic explosion had reached our telescopes,
That
a detector
216.
inside a zinc mine collected the signatures of 11 neutrinos. Born in 1926, Masatoshi Koshiba had originally planned on studying German literature, but after receiving a failing grade in physics, he overheard his teacher speaking ill of his abilities. Spite, it turned out, was a powerful motivator. A month later, he'd raised his grade, enough to pass the requirements for the physics department. When he eventually attended New York's University of Rochester for his PhD, he completed the program in less than 2 years. Fast forward to the 1970s, and Koshiba sought to rewrite the laws of physics. He wanted to observe the
That's not gonna
decay
work.
of protons. He'd hoped to prove the grand unified theory, which sought to unite the two models with which physicists describe the universe: general relativity and quantum mechanics.
Guess I'll have to use the
And
small
this is
one.
what his Kamioka nucleon decay experiment, or Kamioka NDE, was meant to do. A cylindrical tank holding 4,500 tons of water, hidden a kilometer underground.
Alright.
But ultimately, protons proved far too stable. If they ever do break down, it happens so rarely that Koshiba's machine would never be sensitive enough to catch one in the act.
Coupler.
However, he did realize that, with a retrofit, it could be sensitive enough to catch neutrinos
Alright, let's see how
streaming
that's
through
gonna
the
do.
planet. The arrangement of 1,000 photodetectors would also indicate from what direction they were coming. And just 2 months after his experiment began collecting data, Koshiba's team hit the proverbial jackpot. It was actually 2 days after supernova 1987A's light had reached Earth. Researchers at the University of Pennsylvania had sent a fax to their colleagues in Tokyo informing them of the explosion. And it was here they found what they'd been waiting for. For 13 seconds, Kamioka NDE had captured a burst of neutrinos streaming through the Earth.
Fire together.
The timing
Then
had
that
been
one.
perfect. Only a few minutes prior, the detector was shut down for 14 minutes. And
Then
so
that one,
Kamioka
then that's gonna
NDE
fire.
helped open up a new
Then that
era
one, then
of
that's
astronomy,
gonna fire.
which hoped to
Then that,
unveil
then that. Okay.
natural phenomenon too opaque
see how this
for
is gonna
light
do.
to penetrate. And over the last decade, neutrino detectors have been joined by gravitational wave detectors that have helped astronomers explore the mergers of black holes and neutron stars. In 2017, the LIGO gravitational wave detector picked up 100 seconds
Alright,
of
let's see how this
2
goes.
neutron stars spiraling down towards each other and finally merging. Over 17 light-based observatories, including some high above the Earth's surface,
Let me start doing my turn
their telescopes
sooner this
to
time.
the event, collecting information across the electromagnetic spectrum. And an energetic system also allows for the creation of neutrinos. However, unlike supernova 1987A all those years ago, none of the
Start my
neutrinos
turn
captured by
like
Earth's
now.
detectors could be traced back
Gravity
to this
turn.
merger. While disappointing, it was not expected. The event was so brief that
this just above 70.
Slowly but surely, the previously untouchable neutrino is joining the ranks of particles used to study objects throughout the universe. And some scientists believe we can even use these invisible particles to unveil something even more distant.
Coast up to my AP.
The beginning of the universe itself.
Oh, it's my solid rockets are still firing. That's what's up. Okay. My bad. I timed this thing really horribly, didn't I?
This is the cosmic microwave background.
Just turn sideways more.
Our universe's baby picture. The photons captured in this image describe the entire state of the visible cosmos. A mere 380,000
There it
years
is. Alright, now see where
after
we're
the
at.
Big Bang. At this moment, the universe changed from being
Oh, that's
opaque
pretty high,
to
but,
transparent.
you know, whatever.
Over the subsequent
It's okay.
13.7 billion or so years, these photons have touched every corner of the universe in a 45.6 billion light-year radius. And in their travels, their wavelengths have stretched out longer and longer. Today, we can only detect them with radio telescopes. Indeed, they were first detected as a form of static, coming from every possible direction in the sky. By studying the cosmic microwave background,
RCS, I forgot about it again.
CMB, astronomers can turn back the clock to that 380,000 year age. But with light, we can go no further. To peer beyond the CMB, astronomers must rely on a different particle, one which freed itself long before the photon did. They need to capture an image of the C-nu-B, the cosmic neutrino background. As the very first second entered the annals of history, the universe had already experienced quite the cosmic ordeal. It had gone through inflation, distinguished the four fundamental forces, and quarks had either combined to form composite particles,
Man, I really need some more RCS, like it's nobody's business. I can probably just go ahead and fire, and the engine will just correct the rest. Yeah, there you go. Just wait till I get in orbit here. I just don't want to waste this fuel. I just have too much. I don't really need it. And then when this gets above 70, that's all I need. Alrighty. Well, set a target there. Let's just create a maneuver to get out. Plane of the moon. Then I'll find a place where we will interact with the moon's sphere of influence. Alright, now let's whoop, whoop, whoop. Doop, doop, doop. Alright. Well, we're gonna have an encounter there, so cool. Go ahead and yeah, the problem with this burn is like I've still got to turn all the way around, but yeah, once I fire the engines they'll correct the rest of the way, so hopefully I don't have to do this burn too late. I can like turn my engines on a tiny bit just to kind of get this turn moving a little better. Alright, let's just go ahead and just do the full burn. Ooh. stable, but whatever. As long as we get close, it's all good. That's where I should have stopped, but I'm gonna keep going. Dook. There. Alright, let's see how that is gonna go. Oh, did I just destroy my ship? I thought I was destroying like the maneuver. Cool. All right. Well, whatever. Let's add some more RCS. Excuse me. I'm definitely sucking. Do, 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 do. Excuse me. Alright, so I think I'm gonna want like, I think I have 4. Let's do like 6, and then I'll do another 6. Yeah, I'll do another 6 kind of at the bottom. Engines. Was that where I found them? Gotta figure out where they were. Tanks. No, they're not in engines, which is like where I'd expect them to be, I guess, but so communications is a utility. Yeah, there it is. Maybe I should do a bigger one. I mean, I really need to like throw a stabilizer in there. That's what I need to do as well. Well, I can do that. Let me go to the bottom here. First off, I can put a bunch of these guys in there. Then I can come up to here. I can put in like a medium stabilizer. That'll probably help. Alright, we'll see how this does. This will probably do a little better. And again, we got these firing, and that's separating, and then that's separating, and the next one firing, and then that's separating, and then that one firing. That's, okay, everything looks good. Let's try again. Let's skip that countdown. Once I get up to about 150 meters per second, I'll start doing my gravity turn. I'll go ahead and start my gravity turn now. Too much. Let me turn on my RCS. Is it going to help? Is it going to be enough? I should have gone higher and faster. Alright. It's not the end of the world. Get this over 70. Just let my solid rockets take me there, because they will. They'll overshoot me a lot, as usual. Yeah, so just wait for them to burn out. I could have cut my main engines like much sooner. Alright, good. So, let's get out of their way. Cool. Alright, let's see how fast I actually can turn now. prograde. How am I doing with both that stabilizer and the RCS? Is it slightly better? It might be. Anyway. It's time warp to that point. One thing I can do is I can start a maneuver. Like, oh yeah, I just want to get into orbit here. How high is that? Come on. 61, so a little more. How's that? That's good. And I'm about to need to fire. Three, two, one, fire. Trash that maneuver now. Okay. What's all this stuff? Oh, that's my boosters. My solid rock fuel boosters are gonna burn up in the atmosphere here. All right, now let's set this target. Let's get a maneuver started here. Something that'll get us out. Something happened there. Oops. Let's try to do like the minimum fuel that I'll need. That's good enough. Alright, that's gonna be 24 minutes. I want to get off a little early just so I can have time to turn towards my prograde. Let's go one more. 5, 4, 3, 2. Got a lot more RCS, so it's turning me a lot faster than before. It still seems slow, but I'm used to things just kind of zipping around. But it's doing fine. Got another minute until we have to fire. Actually, I need to go towards my maneuver. I forgot about that from the training. Alright. Coming up on the burn. Speed up time a little bit. 3, 2, 1, burn. See how we did. look like it worked at all, but I don't know. Let's just see what happens. Maybe I'm an idiot. Excuse me. Am I gonna get in there? Am I like just out? Alright, let's go prograde and do a tiny little more burn, and then hopefully that will get me a little closer to this moon. Looks like I just need just a tiny bit more. Alright, I'm gonna give it some more gas here. I think I'm doing this wrong. I think I actually want to like get closer to the moon, or just point towards the moon. Basically, I screwed up and I'm trying to fix my mistake at the moment here. Oh, now it's saying I'm going to crash. Is it saying I'm going to crash into the moon at that point? Or is it like where I'm planning on exiting the solar system? Alright, so I'm out of fuel on that. I've screwed up so bad. It's just like, it's like hopeless at this point. Oh gosh. Oh, maybe I've been there and I've just like had the wrong screen on this whole time. Let's create a maneuver. Like, I probably have to slow down like a lot.